Okay, hello, good morning, everyone. So we should be live here. Give me a thumbs up if you can hear me, just to make sure that everything is working. And I will also um, already give you a heads up that I might actually have some internet trouble. I've been having internet trouble over the weekend. So if the stream glitches at some point, which I hope it won't, then you know that that's the reason why it's happening. So so if it glitches, it should be back in a minute or so. Okay. So let's start by today by picking up where we left off last week, which is dynamics of angular motion. We were just about to start that. We did some calculations of moment of inertia, but we didn't get to calculations of dynamics, which is essentially the forces that are, or the consequences of the forces that are working on systems of rotational dynamic or of rotational motion. And of course, as everything in this chapter, we're talking here about fixed axis rotation, so rotation around a single axis that doesn't change over time. So the concept that we're going to introduce here is the concept of torque. And torque is essentially what takes on the role of force in rotational dynamics. And you may be familiar with the word torque, just like you're familiar with the word force. And we're going to turn this into a bit more of a mathematical description. So torque is typically what you think of as a force that is working in some kind of rotational direction, which is of course why it's going to be important here. And the textbook uses this example of opening a door. So we have a hinge here, a door. Excuse me. And we're applying a force against this door. Now, depending on where we apply the force, if we apply the force closer to the hinge, we have to push harder to open the door with the same angular velocity, or with the same angular acceleration, actually. If we push further, and of course that's where the doorknob is for good reason, then we don't have to push as hard. If we push, of course, with a lower force, then again we're going to exert or cause a smaller torque on this door. And then finally, if we push at an angle that is not perpendicular to the door, then we also know that that doesn't have as much of an impact. And there's two different ways to look at this. We can look at this as we're pushing with an angle with respect to the door, or with respect to our vector r here. Oops. Or we can think of this as we're decreasing this r perpendicular, which is the distance from the pivot point to the so-called line of action, which is the line that you're applying the force on. And of course, one thing you also know is that if you push with an angle that is with a force that is parallel to the door, then of course you're not going to get the door to change at all. You're not going to cause any rotational motion to occur. So so this is now what we want to turn into a mathematical description. And it turns out, let me move this over here. So if we look at that mathematically, then in our description of torque, we're going to describe that with a formula where the torque as a vector quantity is the cross product of the position and the force. So does that satisfy our intuitive understanding? Well, what happens if the force is parallel to the vector r? So that's when we're pushing parallel to the door. So if we're pushing parallel to the door, then the torque will indeed be 0 because the cross product of two parallel vectors is 0. So indeed, pushing parallel to the door, there's no torque. We also, of course, see that obviously if we push at a larger distance r, then the torque will be larger. If we push with a larger force, then the torque will be larger as well. When is the torque largest? If I fix the point where I pushed, if I fix the vector r, and if I fix the magnitude of my my force, well, that will be when the force and the position where I push is perpendicular to each other. So in other words, that's when the angle between the point where I push from the pivot point to the point where the force applies, when the angle between the force and that vector is 90 degrees. So in that case, tau is maximized in magnitude, of course. We do have to specify that because there's no such thing as a largest vector. There's such a thing as a vector that's largest in magnitude. If we push right at the hinge, and in other words, r is 0, then of course our torque will be 0. So pushing exactly at the pivot point, that means there will be no torque. Any force that applies at the pivot point, any force that applies directly on axis will cause no torque. And of course, if our magnitude of our point where we apply increases, then equivalently the torque will increase. So this is, if we increase the lever arm, then the torque will increase. So this mathematical description of torque as the cross product of R and F makes sense as it satisfies all of what we think a torque should satisfy. Now, if we look at that on a vector model here, so we have our position vector to the point from the origin or from the axis to the point where the force applies. Then we have our force here. If we take the cross product, we go from R to F with our right hand rule, and then the direction of the torque is going to be where your thumb points. So that's going to be, in this case, along the z direction for a vector R and a vector F, both in the xy plane as indicated here. So that's because the torque is a vector quantity, it will be important to make sure we have the torque pointing in not just the right direction, but in particular to give it the right sense. Is it along the plus z direction or is it along the minus z direction? The direction in which the torque points will be will relate, as we'll see in a couple of minutes, will relate to the change in angular velocity, and then therefore it will be related to the angular acceleration, and so the sign of the torque will be important, the sign along the z-axis here, because it will indicate whether we have an increasing angular velocity or a decreasing angular velocity. So now let's look a little bit more at this r perpendicular. That's the distance from the axis to the line of action, the line along which the force applies. So that's one way to write this expression differently. We can write the torque, the magnitude of the torque, as the magnitude of r times the magnitude of f times the sine of theta, where theta is the angle between the force and the point and the vector from the axis to the point where the force applies. So we can write this also as r sine theta times the magnitude of the force, and that we can then write as r perpendicular times the force. This is, or r perpendicular, because you'll see that this is actually that angle. So the magnitude of r times the sine of theta gives us this opposite side here are perpendicular. So the torque is the product of the perpendicular distance from the axis to the line of action. So that times the magnitude of the force. So that's one way to rewrite this. We can actually rewrite it another way too. The torque is also R in magnitude times F sine theta. Or in this case, we can write this as R times F perpendicular. So what's F perpendicular? F perpendicular, so now this is the magnitude of R times the component of the force that is tangential to the rotation it's tangential to a circle, but you know what I mean. It's tangential to the rotational direction around the axis. So, or it's, in other words, it's the component of the force that is perpendicular to or line that connects to the center of our rotation. So these are two ways in which we are actually more likely to use the expression of torque, because we will know in many cases along which vector direction the torque will have to be, because that we can get just by taking the plane of R and F, and the vector direction has to be perpendicular to it. So what is important then is to calculate the magnitude, and for that we can use the perpendicular distance to the line of action, or we can write it as the lever arm, which is the magnitude of R. So that's equal to the lever arm times the component of the force that is perpendicular. So if we wanted to do that graphically, let's say we have a point here, that's our axis, let's call that our origin. We have a vector R in this direction, and at this point there's a force F that applies. So first of all, in which direction is the torque going to be? It's going to be perpendicular to the plane, and it's going to be pointing out of the plane, because this is my angle. If I point my right hand along this vector direction, along this angular direction, then the torque will be out of the plane, so it will be perpendicular and out of the plane. But now the magnitude we can describe by either using the perpendicular distance to the line of action, R perpendicular, multiplied by the magnitude of the force, or we can use the distance, the lever arm, multiplied with the perpendicular component of the force. Or I guess maybe if I wanted to make this a symmetric drawing, I would actually use this as F perpendicular. So those are the two ways we can write the torque as products of scalar quantities. If we look at the drawing here, this only shows the perpendicular distance to the line of action. It doesn't show the perpendicular component in the perpendicular component of the force. So where is theta in these expressions? Well, theta has been absorbed in R perpendicular or in F perpendicular. This one is F perpendicular. So theta is part of these other quantities that we've constructed from F and from R. The perpendicular distance to the line of action, which is of course going to be different than the total distance to the point where the force applies. And the component of the force that's tangential, which is going to be different from the total magnitude of the force, And in both cases, they're going to be smaller, and they're going to be smaller by exactly this sine theta component. Okay. Let's see. Do I have another slide about that? You know, essentially the same thing here, right? So here we have the perpendicular component of the force would be F, that is the part that's tangential to this circle here. So if I have a component of the force that's in the radial direction, that's not going to contribute to the torque. If the only part that is going to contribute to the torque is going to be the part that is along the direction in which the rotation happens. So that's why, or F perpendicular is the part that is along the tangential direction here. Similarly, again, we could use R perpendicular. R perpendicular would be a distance that goes to the point about here, right? So since F is along the y direction here. Okay. Now, how do we deal with multiple forces applying at multiple places? How do we deal with different kinds of torques? Do we first add the forces? Do we add the vectors R? No, it's much easier than that. To get the total torque, we just add all of the individual torques. So total torque, tau, total is equal to just the sum of all of the individual torques. So that might be, you know, R1 cross F1 plus R2 cross F2 plus, and so on. No need to add up the forces first, and in fact you'd get the wrong result if you add up the forces first. The way to calculate the total torque is to calculate the torque from force 2, calculate the torque from force 3, calculate the torque from force 1, add them all up, and you might end up with a torque that is either in this direction, or the torque might be in the opposite direction, which will be, of course, represented by the fact that you have a positive vector out of the plane here, or a positive vector or a negative vector that would be into the plane, for example, here. Again, you would use your right-hand rule to determine whether a torque in this direction, the counterclockwise direction, would correspond to a torque vector that is pointing out of the plane. A torque in the in the clockwise direction, or in the negative direction, would correspond by the right-hand rule with a torque vector that is pointing into the plane. So now we know how to calculate torque either as a vector using cross product, or we can use our distance, perpendicular distance to the line of action, or we can use the perpendicular component of the force to the lever arm, perpendicular to the lever arm. We can do that for individual forces, and then we can, of course, add them up to get the total force. But of course, the question is, how is that now going to change the rotational motion of, for example, this flywheel here? How does knowing a certain torque, how does that translate into knowing the angular acceleration? First, before we proceed, what are the units of torque? So who can tell me what the units of torque are? So torque is R cross F. So it's going to be in, yes, Newton meters, at least in SI units, right? Maybe some of you are have had to replace a spare tire on your car, and then you know that when you put those lug nuts in, you have to tighten them to a certain torque, and the torque there, of course, is more typically expressed not in Newton meter but in foot-pounds. Yes, exactly. Clearly some of you have had to do this, but the same thing is true, right? Foot-pounds, the foot corresponds to the meter, the distance part. Pounds corresponds to the force. Pounds are used as a common unit for force. But same thing is true. It's force times distance, so the units have to be Newton meter in the SI system. Okay, so now let's see how fast will something start to rotate when a certain torque is applied. So let's go to essentially what is going to be Newton's second law, but for rotational motion. So just as a reminder, I don't need to remind you, but F is equal to m times a. Or actually, the way we wrote that is A is caused by a force over its mass. So if F is equal to m times a, and we know that a, the acceleration, is equal times r times the angular acceleration, both as a scalar quantity and as a vector quantity. Let me just write it as a scalar quantity. So the angular acceleration times the distance from the axis that we're looking is going to give us the linear or tangential acceleration there. So if a is r times alpha, then it means that F will have to be equal to m times r times alpha, right? The torque, which is, let's assume we only have angles of 90 degrees here. So the torque is r times F, and then the sine of 90 degrees, which is 1. That will be m times r squared times alpha, right? I just multiply this previous equation by a factor r. Now we know that m times r squared is our moment of inertia. So that's I times alpha. And so this is now Newton's second law for rotational motion. I'm going to turn this back into a vector quantity. The vector of torque, the total torque on an object, will give us a angular acceleration alpha with a proportionality constant that is the moment of inertia of the object for rotation around that axis. And again, I'd probably want to write this as alpha is tau total over the moment of inertia. So the higher the torque that is applied, the larger the angular acceleration, and the higher the moment of inertia, the smaller that angular acceleration will be for the same torque that is applied. So something that has a large moment of inertia, think a flywheel, which is very heavy, and it takes a lot of effort to make it rotate. That angular acceleration will be small even if you apply the same torque to it as I don't know, a simple wooden disc or something. Okay. Typically we will, just as with F is equal to ma, you'll typically see tau is I times alpha rather than alpha is tau over I. But this is the causal link, right? The tau is causing the acceleration. It's not the acceleration that causes the torque. Okay. So let's use an example for this. Let's see. Finding net torque. We got some problem solving strategy slides here, I guess. I should know because I put them there. But so finding the net torque is what we're going to need to do, of course, for all of the problems where we're talking about finding angular acceleration based on some torque or based on some distribution of forces. So first we're going to typically, almost always, want to pick the coordinate system with the pivot point at the axis, at the origin. Pick the origin of the coordinate system at the pivot point or the axis of rotation. And then we're going to try to find the cross product of R and F for each of the individual forces, and then ultimately sum all of the torques to find the net torque. Once we have that net torque, then we can go to the rotational dynamics part, where we're now essentially in this step here, where we've calculated the total torque, and now we're going to use that to calculate the angular acceleration. Of course, we'll have to have calculated the total moment of inertia as well, right? So let's apply that to an example. We've got this example here. There's someone is applying a torque on a disc, or in other words, someone is trying to get this merry-go-round to rotate. And let's assume we have some information here. So the person is pushing with a force that is 250 newtons tangential. That means that theta is going to be 90 degrees. The angle between R and F is a right angle. Part of the reason is that's just simpler here. We don't need to multiply. We don't need to bring any sine thetas in this problem. It means that the force is entirely in the perpendicular direction. So the full force is the component. And it also means that the distance from the center to the line of action is, or full distance, R. There's no point where this line of action gets closer to the origin than or distance R. So our torque will be F times R in scalar quantities. What else do we know? Well, we have a disk. The disk has a mass of 50 kilograms. That's the merry-go-round. Total weight of the disk is 50 kilograms. And it's got a radius of 1.5 meters. That we will need to calculate our moment of inertia. And so let me write some of these things down. So in the example, that's the example of the merry-go-round. So we have that our torque is R times F. So it's actually R cross F. But in this case, that will be R times F. And in which direction will it be? In this case, because the force is going in this direction, if you use your right hand rule and you put your you have your fingers go from the direction of R to the direction of F, then you will have your thumb pointing out of the ground here. So that's going to be, let's call it Z. So it's pointing in the upwards direction. So now the next part was our moment of inertia. So we have our M and our R, our mass and the radius of the disk. We could go back to that table that we had and find for a solid disk, a uniform solid disk, what is the moment of inertia. And what you would find is that I, in this case, is 1/2 mr squared. And if it's 1/2 mr squared, we can calculate that, plug in our values for M, 50 kilograms, and R is 1.5 meters squared, and we would find 56.25 kilogram meter squared as a moment of inertia. For our torque, incidentally, we would find that this is 1.50 meters times the force of 250 newtons in the z direction, or 375 newtons in the z direction. And so now, of course, we can calculate our alpha. That's the angular acceleration of the merry-go-round. And alpha is tau over I. So this will be 375 newtons along the z direction over 56.25 kilograms meter squared, or 6.67 radians per second squared in the z direction. And I'm writing this as a vector quantity to show you that in this case the vector direction of our angular acceleration will be in the same direction as the vector direction of the torque. So if my torque is pointing out of the ground here along the positive z direction, my angular acceleration will also be out of the ground and pointing in the positive z direction. And so that means that if I now arrange my right hand so that my thumb points along the direction of alpha out of the ground here, then my fingers will indicate in which direction the angular acceleration is pointing, and in which direction the angular velocity is increasing. And so, of course, you'll see that it will increase in this direction that I'm showing here, which is not surprising given the direction of that force vector. That is the direction in which the father is pushing or pulling or making the merry-go-round go round. Of course, we can make this a little bit more complicated by, for example, giving this a little bit more purpose, giving the father a bit more purpose in life by giving the father a child. And the child is sitting on the disk. The child is sitting, let's say, child is 18 kilograms, a mass of 18 kilograms, and sitting at a distance from the center of 1.25 meters. So what changes in this problem? So this was our problem A. What changes in our problem is the moment of inertia. So this will be, let's call it I prime. That's going to be the total moment of inertia of the disk with the child on it. So that's going to be the moment of inertia of the disk, which is what we calculated before, plus the moment of inertia of the child for rotation around that axis. So that's going to be 1/2 mr squared plus the moment of inertia of the child. Let's assume the child is a small child that we can approximate as a point particle. Then this will be mr squared. It will be mass times position, and mass here was 18 kilograms times 1.25 meters squared for the distance from the center of rotation. Again, tau is the same, so we can calculate alpha as tau over now I prime. Now if we do that, we'll find, well, let's see, we could actually, obviously we're going to find a larger moment of inertia here. It's going to be 84.38 kilograms meters squared. So a larger moment of inertia will give us now a smaller angular acceleration. It will be 44.44 radians per second squared, still in the z direction. So what does this mean now? What could we do with this this quantity alpha? Well, one thing we could calculate, and this is one of the places where on an exam we would have you calculate this, and then as a next step there could be a question: how long does it take? How long does it take to complete the first turn? And I'm not making this up. I've asked this question before, exactly about the same problem with a merry-go-round. So how long does it take to complete the first turn? Well, what would we use? We would use the formula that theta is theta 0 plus omega 0 times delta t plus 1/2 alpha times delta t squared, right? That would be the formula that that we would use here. And so in this case, we'll start at 0. We want to get, for the first turn, we'll get to theta of 2 pi. I would probably put here that we start from rest. So this is going to be 0. And then we can calculate delta t is going to be 2 times delta theta, or 2 pi, over alpha with a square root. And we can calculate that, and we would find a certain amount of time. I didn't do the calculation here, so I can't tell you what it's supposed to be, but that's one of the kind of problems that we will be able to encounter using this using these formulas based on torque, based on calculation of a moment of inertia, and then using the formulas that we calculated for kinematics, which in this case we can use here because of course alpha is constant. And those formulas are only valid when alpha is constant. Okay, so that's an example of a problem here. In dynamics of linear systems, we've also used energy, work and energy, to calculate some of the problems there, right? So we can do the same thing, of course, in rotational problems. So how do we calculate work that is being done? So we've already calculated one thing, which was how to calculate Where's my cursor here? There it is. So we've already calculated kinetic energy, and so we know that work to go from a point A to point B will be the difference in kinetic energy for point A to point B, with a kinetic energy or situation A and situation B, where the kinetic energy is 1/2 I omega squared, now in the case of rotational motion. What we don't have yet is another way to calculate the work. In the case of linear motion, we had that the work was F dot dl along some trajectory that we're calculating. Let me call it not dl. Let me call it ds. Some trajectory, some point from some point A to point B. We have in a little vectors ds here, and there's a force that applies along that trajectory, and there could be an angle theta here, so we have to consider the direction here. Now we can start from this and use it to calculate the work for rotational problems. And we'll start from this, and we'll write the work is from A to B, or force dot ds. But what we know is that S is theta cross r, one of those expressions that we've used to draw the parallel between linear motion and angular motion. You might remember we then changed this to the tangential velocity is omega cross r, and we introduced the tangential acceleration, which is the angular acceleration cross r. So we're going to use this one here, the first one, because if that is S, then ds will be d theta cross r, where I've made a little bit of a simplification here because I've assumed that dr is equal to 0. Since we're on a rotational motion, this makes sense because any dr will be along the r direction, and so okay, let me not write dr is equal to 0. Let me write that dr is parallel to r. So if I properly apply the chain rule, then the terms with dr would drop out. But in any case, I can write ds as d theta cross r. So this is going to be now an integral from A to B of f dot d theta cross r. And I imagine you can see where this is going. I'm now going to use the fact that I can rearrange these terms in this triple product. If you've not seen triple product, no worries. But if you have seen triple product, you know I can sort of rearrange these terms without introducing any change. So I can write this as the integral from A to B of d theta dot r cross f. And this, of course, is useful because this now gets me my torque in this expression. So it's going to turn out to be A, B, torque dot d theta. That is the expression for work in rotational coordinates, in rotational dynamics. Of course, it looks like a complicated integral, but for tau constant, which is one of the common situations, W will just be tau dot delta theta from A to B. So if I have delta theta from A to B is, let's say this is one rotation. During one rotation, the amount of work that is done is tau times 2 pi, and if we just work around the same axis, then I'm just going to use a scalar quantity. Oops, that's not an eraser. I'm just going to use a scalar quantity tau here. So that allows us to calculate the work, which we now can use to calculate the change in kinetic energy from A to B. And for example, we can calculate the kinetic energy at point B, and that we use then to calculate the angular velocity at point B. One other part to this, since we're at 10:21 already, the last part is that we can also calculate the power, which, as you remember, is the change in work per unit time, or the work done per unit time. And since we have that this is that the work is tau times delta theta, this will actually turn into tau times d theta dt, or tau times omega. So power in rotational systems is torque times omega, which, as you might remember in linear systems, was the power in linear systems was F times V. So again, V is omega and tau is F. So there's again a parallel between those different formulas. Okay, that's it for today. So we'll continue with this, and in particular, we're going to start applying that in problems and talk about angular momentum next in the next chapter on Wednesday. So so make sure you remain caught up, even though I know you're working on finals as well for some of your other courses. So don't ignore this course completely. Or you're going to have a lot of work to do catching up over the break after finals. Okay, that's it for today. Talk to you all on Wednesday.